Hello all and welcome back. So in this video, let us continue our discussion and now let's see how can we implement graph in our code. Now in the last few videos, we have discussed about what exactly a graph is, different terminologies in my graph and different kinds of graph which are available to us. Now let's talk about implementation. There is one thing more which I would like to mention. Majorly the concepts and question around graph are very easy and doable. Just the problem which I find in most of the student is that because it is taught a lot late into your journey of DSA, many student gets majorly overwhelmed by all the other data structures they have studied, and because it is a little bit complex than other one which we study normally. Okay, it has many data structures and kind basically getting used at a single time, and because many have not done the practice, they are always afraid of graphs, right? You don't have to do that. Please make sure that you are just starting this with a very fresh mind. For the time being, just have the basic idea about all the data structure. Okay, don't get overwhelmed, because else you will always face an issue and there will be a permanent fear of questions with graph, which I don't want any of you should have. I have done graphs a lot in depth. More than 50 plus questions I have attempted on graphs, and they are easily doable if you are just able to understand it once pretty well. Okay, great. Also, now with that said, let us now start with graph implementation. Before we begin to code again, we are going to discuss how exactly can we do that. If you remember about a tree, which was very analogous and is actually a kind of a graph, in tree we used to have some property that there will never be a cycle. It was hierarchical in nature. So we saw that how tree, we always used to have something like this, right? So they were all hierarchical in nature. We have things like this. Now what happens in a graph is that I don't have any such hierarchy. The nodes are all independent. It can very well happen that a node is not even connected to any other node. It is just mentioned or present here. And we can draw a graph similarly like this. So let me make a node and let us make some multiple nodes. Now, if we think about this, irrespective of all the properties, all the different kind of graph, what actually make graph a graph is are two things, right? So the very first one are the nodes, and second are the edges. Now, different combination of this edge, different combination of these connections give rise to different types of graph. But the basic idea is that if you are able to tell that, hey, these are my nodes and they are connected like in this manner, then I think we can be very much confident in saying that this is how your graph should be. Okay, so these are the two information which in a way define your overall graph. So for this overall, for this thing, what we can do now, let us talk about in terms of implementation. We should in some way or other have a class graph. In this class, okay, I should have the overall information about my nodes or vertices. Normally we take vertices, okay, in our implementation. So nodes also you can take, that should be fine, but you will see at many places on even competition vertices are taken. So I believe that we have done that nicely. And the second one is edges. Now let us talk about, are there different ways through which we can actually take these things, the nodes and the edges, right? So the very first and the easy over the shelf thing which I would say is the approach, where what I'm going to do is store the vertices and store all the edges. So pretty straightforward. What I'm saying effectively is that I'm going to store all my vertices, right? That is one thing which I have. Along with that, I will store all my edges. Now, normally we will be storing edge in a tuple, right? So if let's say, if I just go back and show you in an example, or let me draw one example here on the right. Let's say this is my one node. Let us create multiple such nodes. Now, what can I do here, everyone? Is that if let's say it is 1, 2, 3, and 4. If it is connected like this, Let's say 2, 3 are connected like this. Then nodes or vertices are straightforward. I can say that I have 1, 2, 3, and 4. 4 nodes are there. Even what we can do, we can, if they are not labeled specifically with, let's say, A, B, C, D, we can just take them normally as well, right? So we can have them 0 index. That should be fine. Because now it doesn't matter which one is 0, which one is 2. Second thing is, I can store the overall edges, something like this. So let's say 1 comma 4, it's a tuple, and I can store 2 comma 3. Now, if you know that there are these many edges, if you know that there are these many vertices, then you can draw your graph pretty well, right? Now, many of you might be thinking that why are we storing number of vertices? Can't we get it from here? Well, yes, you can. But what will you do if there is some 5 which is not connected to any? Okay, so your vertices will have this information that there are 5 vertices, but the connected are just the 2 ones. Okay, pretty straightforward, I believe. Should be all fine. So let us try to implement this once and then we will move on to the next one. So as to understand each and every one a lot in depth. One more thing, I have not seen this kind of a explanation in anywhere because normally what happens is that this is not used, but I want to make sure that you understand each and everything in a very much depth. Okay. Great. So let us try to implement this, everyone. And this approach, like overall way of storing, is known as something called edge list. Okay. So edge list. For each and every edge, I am just maintaining it into a list. So let us start. Now, what we can do, class graph using edge list. We have some vertices, right? So self dot vertices, and let me take it V only is a list of vertices, or we can take it dictionary. That would be better as well, right? Because we already know that we can store it in this way, right? So what we are going to do, everyone, and the edges can be self dot edges, which will be a list. And this will also actually be a list only, not dictionary, because dictionary I will have key value pairs. But here we are going to say that, okay, 1, 4, 2, 3, and 5. These are my nodes. Great. So this is the first thing. Let me have it in a constructor self. Great. So now we have placeholder for edges and vertices, right, everyone? Now what if we can do next is def add vertex, right? So in this, what we can do, we can just ask for a particular single vertex and we have to just add that. So when I will be trying to make my overall graph, I will say that, hey, I want 1 as a vertex, I want A as a vertex, and this I'm making sure that you implement in a way that it can be labeled as well, right, everyone? So self vertex, okay. First, let us check if vertex not in self dot v. What we can do? Self dot v. We can append my vertex here. So let's say here, let me just remove everything. Yeah. So pay attention, everyone. Let's say what's going to happen. If you're trying to make a graph, let's say A, B, you can say that, hey, add A. But what if A is already there? Then we, of course, cannot do that. Okay. Great. So let us move forward, everyone. If this is done, we can add a vertex and we can say return. Because I don't think anything we have to do. Maybe just for good coding practice, we can print vertex already exists. Great. So let us move forward now, everyone. The next one is again with the add edge. So now what we have to do, we have to add an edge. For this, what I'm going to take source destination. And yeah, that should be fine. Let us add it. If source in self dot vertices, self dot v, and destination in self dot v, then only we should add it, right? So again, these are the kind of thing which many people miss out when they are making their graphs. The understanding again is that if you want me to have a edge between A and B, then you should have those vertices in your graph, right? We are trying to make sure that the overall implementation is complete. So if you want that, then I want to make sure that this particular A and B both are present. Else, how can I make a connection or an edge between them? If that is done, then what we can do? Pretty easy implementation, as I said, edges dot append. Now, what I'm going to do to make it a lot more clear for all of you, pay attention. We can make a edge, which is a tuple of source and destination. Okay. And we can just add this edge here. So I hope this is clear, everyone. We have just added an edge which we created. We are creating it a tuple because of two reasons. It will not be edited. Second, it is easier to just see that if this tuple will overall be present in my this list, because tuples are not mutable. So we can very easily check if they are present or not. One more thing which all of you can do. We can also have something known as weight here. Okay. Now, what is the benefit of weight? If you all can tell me, let me just explain that as well. So pay attention, everyone. If we just want to have a weighted graph, now instead of a normal graph, what can I do? I can have this A here. I can have this B here. I am just saying that if the user provides the weight, that is fine. If not, I will take it as 1. So you can make your whole graph. You can make your whole graph. Or let me make it C. And not provide any weight. And I'm going to say that, okay, it's a unweighted graph where I'm just taking the weight as 1, or it doesn't matter even, right? But if you will provide that weight, then that is something which I'm going to use. So pretty sure that this must be also clear. That is why we can define a weight here as well. Let me just remove everything. If this is not the case, then again with good coding practice, print 1 or both the vertices are not found. Great. So let us move forward, everyone. Now we have made our graph. So we have the add vertex here and we have the add edge here. Okay. Now the next thing, at this point, actually, we can even see the graph, like we can create a graph. So graph equals graph using edge list, graph dot, let us see which kind of a graph we have to make. Okay. So let's say I am making a graph where this is 1 and this is 2, this is 3. We are adding this, and let's say we are adding this connection. Okay. So pretty straightforward, not doing anything, just 3 nodes are there and I'm making 2 connections. So, and because connections, we are saying that they are directional. So we have to make sure that we tell them in this particular format. One thing, why are they directional? Because I've taken source and destination. If I would be adding edge equals destination and source as well as destination and source like this as well, then it will become a bidirectional graph, because I am saying that, hey, I want an edge which goes from source to destination and an edge which goes from destination to source. Here we are not doing the same, so it's a directional overall graph. Okay, I think we mistakenly like erase that, no worries. We have 1 here and we have 2 here, and let us make 3. Great. So let's see what all we are doing here, everyone. Graph dot add vertex 1, add vertex 2, add vertex 3. 3 vertices are added. Graph dot add edge. Edge, I am adding a unweighted one from 1 to 2, and graph dot add edge from 2 to 3. So in a way, what all we discussed till now, I think we have successfully just be able to write the same in my node. Oh, sorry, in my code. Right, everyone? What do I mean by that? If you will see, you see this particular graph based on all the terminologies, everything which we discussed, we are able to say that, okay, a graph is made. Now to showcase that, to see this again, we will have to make sure that we are able to write a display function as well. So let us start with that. Def display. Okay. Again, I will be getting just self here because everything is with me only. Great. So first thing, print vertices I'm just saying that, okay, I will print out the vertices for you as well. So you can see. So for vertex in self.v, all I'm going to do, print vertex, okay, something like this. So you can see the vertex pretty nicely, everyone. Great. Vertex majorly I'm showing to make sure that if let's say there is 4 as well, so we should be aware that, okay, just we are showing each and every vertex, because if we just show the edges, then that 4 can get left behind because there is no edge. It's a isolated node. For my edges, for source and source, destination, and I think weight was there as well. In self dot edges. So pay attention, everyone. This is just I'm doing a tuple unboxing, right? So where we have a tuple, we are able to actually load it and unloading, not unboxing, unloading. So I'm able to just say that, okay, I added these 3 things in my edge. I want to now access my this edge. So I will have to make sure that I unpack it also in a 3 things, 3 variables I have. If this is the case, then what we can do, print again F formatting, source, source, and let us make it like this. Destination, destination. I'm just assuming a weighted, unweighted graph as of now. So I think that should be fine. And we can do one more thing actually. We let us remove that so that it is a lot more clear and easily readable. Great. I think, yeah, let us run this. What we will do is we will try to create this graph based on the way we can see it. So we will just make sure that we are able to create the graph again, and it is exactly the same. Let me run this now. Let me remove this. So just have it drawn at your end once after pausing. Great. Now it is saying to me that, okay, it has 3 vertices. Let me just draw these 3 vertices. 1, 2, and 3. It is saying that 1 to 2, draw one vertex. 2 to 3, draw, 1 to 2 and edge, 2 to 3 and edge. And I think, yeah, we are able to very nicely make our graph from this particular approach as well. Now, one thing to note here, let me just ask you a question now, everyone. Let's say if I'm using this particular graph for a particular city, or let's say in a social network, pause the video and think that what can be the pitfalls or some limitations of this kind of a structure. Now, if you would have thought after pausing the video, then you must have realized that I am maintaining these edges, that is fine. But how many edges can I have? Let us see that. So the question is, how many edges in a n node complete graph? I think the answer for this will be something like this, NC2. For each and every, from these nodes, I can select 2 nodes and draw a edge between them, which comes out to be something like n into n minus 1 by 2. Okay. So what I'm saying, if this is my graph overall, let's say it is having 5 nodes, then I can select any 2 nodes and make an edge between them, right? So it is just selecting 2 nodes out of n, which is nothing but NC2, right? This gets back into this formula if we just unpack it. Now this means that I can have a edge list which can be having a overall length of something of the form n square. So any algorithm which I'm working, which I'm writing for my graph. So let's say tomorrow I'm asking you that, hey, are these two friends, like they have an edge between them? You will have to make sure that you run through the whole edge list. And I think you can understand that why it's bad, right? So we are dealing with a n square complexity here for just finding out a very simple operation. If there exists an edge between 2 nodes, you will have to go through each and every edge. Something which I think is very bad. If Instagram would have applied this particular approach, it would never have been able to efficiently find out who is following whom, because for every time it has to go through the n square overall approach. Okay, so I hope all of you are able to understand how bad it is. So that's why, that is the reason edge list is never used. Now I wanted to make sure that you understand two things. First, many people don't implement this, but I still made sure that this is clear because this is the easiest implementation which one can think of, right? Second, yes, it is not used, but now I hope it will be a lot clear that why exactly it is not used. Okay. So again, it is very important to know about this, but edge list we will never be using because of this issue in complexity, right? There is something known as adjacency list and adjacency matrix, something which we are going to see in the videos moving forward. Those are majorly the one which are used, everyone. Okay, so let's meet in the next video. Pretty sure that you must have understood each and everything in this particular video. I have taken it very slow, made sure that even explain things which no one tries to, so that you have a very good idea from for graph as you learn it with me. Okay, so cool everyone. Now let us meet in the next video where we will see the other approaches we can define our graph.